This video looks more deeply at the scalar quantity b and its role in determining the time-like or otherwise of possible world lines that can be followed by objects with mass within the ring singularity of the Kerr space-time. When I say the quantity b, I'm referring to the quantity shown in previous videos prior to this. It shows how this quantity is affected by the parameters of mass, radial distance within the ring, and the angular momentum per unit mass of the black hole. Alright, so end of the last video, we've come up with this curve, right, within the ring singularity region, curve of constant radius, and we showed how it moves, how the time coordinate becomes increasingly negative as the object, be it particle or observer, moves forward in their proper time. As their proper time increases, they move down this curve. The tangent vector, the forward velocity to this curve, is given by this object here. And as they move forward, future pointing into the future of the observer or the particle, they move down this curve, and this Boyer-Lindquist coordinate here becomes increasingly negative. Okay, and remember this is constant radius here within the ring singularity. This occurs all within the azimuthal plane, so theta is pi on 2. All right, and there were two directions for B. There was rotation clockwise, okay, in the negative angular direction, looked at from above. And for plus B, we have rotation in the positive direction, which is the anti-clockwise direction, or the conventional sense, looking down from above from the positive Z direction down. Okay, so at the ring singularity in the azimuthal plane, theta is pi on 2. We're going, the ring singularity occurs at r equals 0, the red line here, the red broken line here, r equals 0. Outside that broken line, r is greater than 0. Inside, r becomes less than 0. And so we're going to pick a circular orbit within that ring at minus r0. The ring has radius a, which is the angular momentum per unit mass, which has units of meters. And plus b is rotation in the positive angular sense, looking from down from the positive Z direction. And minus b is counterclockwise, as looked from above, looking down from above from positive Z. Image shown is a constant time slice, t equals t0. Okay, this singularity occurs at z equals 0. It's described by the equation x squared plus y squared is a squared. Okay, here's the angular direction, positive being anti-clockwise around. Now, we define B to be the derivative of the angular coordinate. That's the fourth coordinate in the Boyer-Lindquist set of coordinates, using CT, R, theta, and phi. And this is the derivative, B is the derivative with respect to the proper time. So the change of the angular coordinates. So here's a particle, an observer on this green line, following this trajectory here, following this orbit, going around. Okay, d phi dt, okay, is the derivative of the angular coordinate here with respect to the proper time of the observer or the particle. That's a watch they carry with them, if you like, or a timepiece they carry with them, and they record their own time. Now, using the chain rule, we can break this down to d phi dt, the coordinate time, times dt d tau, the proper time. Okay, dt d tau is the Lorentz factor, gamma L, which I will use gamma to denote the curve and gamma subscript L to denote the Lorentz factor. So dt d tau is the Lorentz factor, okay, and the coordinate angular velocity is d phi dt, okay, as opposed to the proper angular velocity d phi d tau. Okay, the sign of B is determined by the sign of the coordinate angular velocity. So it can be in the positive direction, anti-clockwise, or in the negative direction, clockwise. Okay, so we define B to be d phi d tau with the chain rule, gives us d phi dt, coordinate time, dt d tau. Okay, now that leads to dt d tau. The Lorentz factor is, rearranging above, is B times d phi dt, the coordinate angular velocity, the reciprocal of the coordinate angular velocity. And we'll call that, as I have in previous videos, I'll just call that reciprocal of alpha inverse. And I do that just to simplify the algebra on the page in front of the screen you're viewing. But alpha inverse is just the reciprocal of the angular coordinate velocity, the coordinate angular velocity. So alpha inverse is this object here. dt d tau is the Lorentz factor, Lorentz gamma factor, one on this object here. Okay, with the usual speed v of the relative speed with respect of one frame to the other. Now, so our tangent vector or fall velocity for our massive particle, be it an observer or a particle, but an object with mass, gamma prime of dash is the fall velocity, or the tangent vector here is this object here. We can rewrite this as b times alpha inverse is dt d tau, so c times dt d tau, and b is d phi d tau as defined. Now, leaving that as c dt d tau, over here we can again apply the chain rule here to give us d phi dt d tau. Okay, and our tangent vector or fall velocity of our massive particle, gamma prime or gamma dash, is c times dt d tau basis vector et plus d phi dt d tau basis vector e phi. The components here, expressing the vector in component form, we have, because it's derivative of this constant here, which is the fixed radius within the ring, a negative quantity, its derivative is 0. This is a fixed as a polar angle, theta is pi on 2, so its derivative is 0. Okay, writing it using the basis vectors, we don't need to include the zeros, of course. All right, now, so our particles world line is given by, if we anti-differentiate our curve to find the integral curves to this vector field, which is gamma prime is the vector field, so the integral curves to it. Anti-derivative back, here's our curve, this object here, we all found this in the last video. Substituting in here c dt d tau times tau, we have all this object here. Okay, this was found in previous videos. Now, for speeds very close to that of light, we have, for example, a v is here, I think I've got 10 nines in here, so really, really close, very, very close, arbitrarily close if you like, to the speed of light. The gamma factor becomes huge, 70,710.6. Now, which means 1 second of proper time for the particle or observer is equal to delta tau is 1 second. That tells us that delta t, the coordinate time, is dt d tau times delta tau. It gives us minus 70,710.6 seconds. And yes, I did say minus because I'm using the value up here. Remember, we found that this, we found a curve that travels backwards in time. Within the ring singularity, this sort of violation of causality is allowed. All that's the subject of the last couple of videos, so I won't go into that again, but just showing you here that for a very large Lorentz factor, this Boyer-Lindquist time coordinate here can become very, very large. Okay, that's 1 second gives us that. If we were to continue to travel on this curve for a month at the speed here, okay, then delta t becomes that many months, 70,710.6 months, which is 5,892.6 years backwards in time into the past. Okay, now all of these results, as we found in the last video, hold so long as the curve is time-like, because anything with mass must follow a time-like curve. Photons can follow, and other massless particles can follow a light-like or null curve, but anything with mass must follow a time-like curve, otherwise this doesn't happen. Now, we found this to be the case in the video prior to this one, but there is one slight small exception. Now, just remind you, in that last video, the previous video here, we had to show that the fall velocity or tangent vector is time-like, which means then that the curve to which it is tangent is also time-like. Okay, so we did all this algebra. This slide comes exactly from the last video, and we got down to this result here and concluded that this first term dominates the second one, and so overall this inner product, dot product, scalar product, is negative. The result of it is negative, it's less than 0. Okay, but, and we took that therefore as evidence that gamma prime is this curve we've been talking about is light-like, not light-like, sorry, my apologies, time-like. Okay, but is that true for all values? Are there any possible values, for instance, see this alpha, the reciprocal of alpha, that's the reciprocal of the angular coordinate velocity squared, okay? Could that become so small and reduce this first term very, very close to 0, such that the second term, which is clearly positive, dominates? and therefore this ceases to be a time-like curve because this result then becomes greater than 0. Is that possible? Could this alpha become the reciprocal? Alpha here becomes so small that this is reduced to something that is less than the second term here. And that can happen, and we'll see that, okay? For much of the coordinate angular velocities, as I'll show you with some plots, that's not the case, but there are values for which it is true, and this curve then ceases to be time-like. Okay, now, important, the central argument to all these videos is that the curve on which this object within the ring singularity travels is time-like. Okay. Now, so our tangent vector is this object here, written in the basis vectors, this object here, okay? So to be time-like, we need, remember, the inner product, the scalar product, dot product, the contraction of the vector under the metric, to be negative, okay? So let's put that in here, this dotted with that. Expanding that out, we get all this here. Okay, we can take out a common factor dt d tau there. So we take out a product of two of those. So dt d tau, the Lorentz factor squared. Now the Lorentz factor is always positive, the square of it's always going to be positive. So what we're left with here is this object here inside once we do that. Okay, coordinate angular velocity squared, coordinate angular velocity here. We have the basis vectors, which the product of those contraction under the metric gives us the metric components. So I'm just going to rewrite this around. So I'll put this last term first. So g phi d phi dt squared plus 2c gt phi d phi dt plus c squared gtt. Now, this g phi, remember, is negative for values of r within the ring singularity. I've shown all that in past videos. Okay, this GTT is also negative, but this GT phi is positive in the middle here. Okay, now we require for the curve gamma prime, for the tangent vector or forward velocity gamma prime to be time-like, we require this inner product or dot product to be negative, the result of it to give us a quantity that is negative, okay, less than 0. Okay, well, dt d tau is not negative, and the square of it's definitely not negative. So we're only left with this object here. Now, this looks like a quadratic expression, I should say, not equation, but a quadratic expression. And it's actually, because this is less than 0, it's actually concave down, so it's pointing down. So we've got a vertex at the top, and the curve points downwards, opens up downwards. Okay, so let's have a look at that. Okay, so we'll give this object a name, we'll call it f. So when I plot f, I'm talking about this quadratic expression here, and we want to know where is this less than 0. Now bear in mind GTT is this object here, which is less than 0 for all values within the ring singularity, R0 here. Remember, it's minus R0, so the minus that was here becomes positive, and this whole thing is negative. For R0, this changes sign and becomes a positive term. And for R0 small, remember these are very small values. If you look back to the previous videos, you'll have to watch these videos first prior to this. But we've chosen R0 to be very small, just inside the ring singularity, very small, so that this negative term dominates these first two terms. Okay, so that's less than 0 for very small values. Now this quadratic is inverted, so concave down, if you like, because the leading term g phi is negative. So it's got this shape here, and we expect two intercepts. Okay, much of the curve lies with in the region where f is less than 0, where f is negative. It has two intercepts where f equals 0. Okay, and there's a region of values where the coordinate angular velocity results in f being a positive expression, and therefore the curve cannot be time-like. So these values here between these two intercepts render the curve space-like. No particle with mass, or even a massless particle, can travel on a space-like curve. It's not possible. Okay, so its intercepts are found by setting f to 0, equal to 0, and using the quadratic formula we get two roots here. Okay, in terms of the metric terms gives us this. Okay, what we're going to do now is look at a couple of examples here, and I'm going to use a 2.1 billion solar mass black hole with dimensionless spin parameter A star is 0.44, R0 is 0.18, which gives you this many meters. Okay, so that many meters inside the Now remember, this is minus r0. I'm just quoting you the r0 part. So we're inside the ring singularity, and we've gone in by this distance here, 1.36204 times 10 to the 12 meters. Okay, so that's our black hole, a 2.1 billion solar mass one. Okay, so we plot it, F, with respect to the coordinate angular velocity, d phi dt, and we find that for much of it, it's negative. But here there are two intercepts, and at this point, F becomes 0, and so our curve goes from time-like all along this axis. These two intercepts, these two values, give us a curve that is light-like. So particles with mass, objects with mass, such as an observer, cannot travel on that. Only massless particles can. And then between these two intercepts, this quadratic expression becomes positive, and so our curve ceases to be time-like, it ceases to be light-like, it becomes space-like. Nothing can travel on that. So effectively, there's an upper limit to our coordinate angular velocity, and that is this intercept here. We can't go beyond that because the curve upon which we travel, the curve upon which the observer travels, becomes space-like. So it's not possible. Just a reminder, I'll pick up this again, but we can convert angular velocity to linear velocity. So the linear velocity of something moving on a circle is the radius region. I'll show you why I'm using that, times the angular velocity, this bit here, and that gives you the linear velocity. That's at each point tangent to the circle. If the object suddenly left the circle and traveled in a straight line, its linear velocity would be given by this object here. Remember, d phi dt is the angular velocity because it can have a positive or negative value as well as the magnitude. Okay, the two roots are d phi minus, the lower one, is this here, and the upper one, this one here, is this one. Now, and the linear velocities at these points give us 2.43 times 10 to the 8 meters per second. That's about 0.81 c. And this one here, when we calculate that, we end up with something larger, 1.07 c. So greater than the speed of light, so not really acceptable. This isn't a possible result, so we need to restrict our domain as a result of that. Okay, so let's just remind ourselves of the geometry of the ring singularity here. D phi dt, that's is in units of radians per second. That's the coordinate angular velocity, radians per second, is v on a minus r0. Where did I get a minus r0? Well, the ring singularity itself has radius a. We're choosing a region just inside, so this green circle here is meant to be just inside, close to the ring singularity, but just inside, so the r0 is small but negative. Okay, hence this is a negative coordinate in here up to here. And so our observer traveling along this orbit, along this world line, is our observer or our particle traveling on this world line just inside the ring singularity. There's its linear velocity v. Okay, a minus r0 is radius, because to the radius a we add this negative quantity here. This takes us down to the green circle here. Okay, here's our angular coordinate here. A minus r0 is our radial value, if you like. So our v linear becomes a minus r times d phi dt. Okay. Plus b is in the conventional positive angular direction, minus b in the negative angular direction. All right, now if we limit the allowed range of linear velocities to v is greater than minus c, that's in the negative direction, and less than c in the positive direction, it can't be equal to c because only massless particles could travel at c, so that's not acceptable for a particle with mass. And the plot of the permissible range of angular velocities is this endpoint here in the positive region above the axis. That is a linear speed at this point of c, and over here minus c, okay, in the negative direction. Most of the curve is in the f is less than 0, f in the negative region, negative range, and so our curves are all time-like. At the intercept, the curve becomes light-like or null, and beyond that becomes space-like. So there's clearly a small range of positive angular velocities, that's up here, for which the tangent vector and its integral curve are not time-like, and that's from the intercept onwards. So that sets an upper limit on the angular velocity. Okay, so the allowable domain over which graphs like these can be plotted is this one. It's the set of points defined to t, a set of values defined to t, lying between minus that and that, not including those endpoints because we're not traveling at the speed of light. Okay, so let's now look at some more examples. So our second example is a 21.2 solar mass black hole. It's based on an actual black hole that I took from the literature with dimensional spin parameter A star is 0.9985. So it's almost an extreme Kerr black hole. R is 0.1 of A inside the circle, so it's 0.1 of the radial coordinate A, which is that many meters. And it's got this following plot here. Again, we have an intercept and a region above the axis. C over A minus R0 is the endpoint here, and minus C over A minus R0 is the endpoint here. So that's the domain over which we plotted it. Okay. Now, it has roots at phi dt. That's the first root. The second one's not relevant because that's where the curve has gone space-like. Yeah, it's in that region, and that region is not accessible to objects that must follow a time-like curve, which is all particles with mass. Now these correspond to linear velocities at these points of here, 0.8, 78% the speed of light, and this one here, 120% the speed of light, which is not possible. Again, only the first intercept is physically allowable. Notice there's a restriction on how fast we can travel into the future, whereas the only limit on how fast we can travel into the past is set by the upper limit of the linear speed, which must be less than c. So we can have linear speeds up to and less than the speed of light, if we have mass. Okay, whereas here in the positive direction, we're limited only to about 78% the speed of light. Now in the two examples above, the upper limit on the linear speed of the observer or particle travelling into the future is 0.81 c, or 81% the speed of light and 78% the speed of light. This places the limit on how large the Lorentz factor can become, because if V is 0.78 c, then gamma is 1.598. The Lorentz factor is 1.598. Now compare this with the case of travelling into the past, where the Lorentz factor can become very large as the speed of light is closely approached. So for instance, if we take V we can go beyond, if we're travelling into the past, we can go beyond a speed of 78% the speed of light. We can go arbitrarily close to c here because there's not that limit to give us this gamma factor of 4.75 times 10 to the 7. So, okay, so let's imagine we have a spaceship that's traveling at this speed here, okay, with observers in it, and they travel at that speed for a month. Delta t becomes minus dt d tau delta tau. Remember, we're traveling backwards in time, is 4.75 times 10 to the 7 months, which is 3.96 million years into the past. All right. Traveling forward, the Lorentz factor is limited in how high I can get, because we're only getting to about 78, 81% the speed of light. Okay, so Sagittarius A star has a mass of 4.2. That's the black hole in our Milky Way galaxy is 4.2 million solar masses. Dimensional spin parameter of 0.44. If we choose R as 0.1a, we get that many meters. Okay, it has roots d phi dt, this and this one. Its permissible speed, again, we only pick up the first one. Second one gives us a non-physical result. Its permissible speed is 2.427 times 10 to the 8 meters per second, about 81% the speed of light. Okay, its plot looks like this. Now we can have arbitrarily large values in the negative direction, traveling backwards in time, but there's an upper limit on how far or how fast we can move into the future because of this intercept here. The actual speed of light is up to here. That's where the domain ends. But there's a whole region that's not accessible because world lines are not time-like here. So the greater an object's angular speed, the faster it can travel into the future or the past. So you imagine a spaceship on that circular green orbit. The faster it goes, the quicker it'll travel into the past or into the future. But in terms of the future, there seems to be an upper limit. All right. there is an upper limit to how quickly an object can travel into the future with its maximum angular speed given by d phi dt into the future. Remember, this is positive. Is this intercept here? Remember, that was that first intercept we saw on the graph on the left. Beyond this angular speed, its four velocity vector ceases to be time-like, which means its world line also ceases to be time-like. And so that region, those speeds there are not accessible to us, not accessible to objects with mass. Particles with mass must travel on time-like curves, but there are a larger range of angular speeds allowed when traveling into the past. Okay, maximum angular speed for traveling into the past is given by this. It's got to be greater than that minus c on a minus r0. Not equal to, massless particles could make that equal to, but for objects with mass it must be less than that. So it's got to be, that's the lower limit, and it's got to be greater than that if it's a particle with mass. Its absolute value, if you like, is less than c over that, because we can't, an object with mass can't travel at the speed of light. Okay, now for the features of the plot of f in general, reminding here's our f, this is that quadratic on which all this argument rests. Okay, we have, here's our domain here, it's the lower limit. A light-like or massless particle could reach that speed. Again, a massless particle can reach this speed. But for our time travelers, going into the past, negative values here are all allowed, no problems here, right up to and arbitrarily close to the speed of light, okay, in the clockwise direction of rotation. But this intercept here, at this point, the curve goes, f is equal to 0. Below this point, f is less than 0, and so we have time-like curves. At this point, at that single value, the curve becomes light-like or null. Beyond that value, the curve becomes space-like, and so inaccessible to any object with mass trying to travel along it. It's not possible. So it can't reach that top end of the domain there. Okay. Now we define B as d phi dt, this rate of change of the angular coordinate with respect to proper time. And with the chain rule, d phi dt, dt d tau, which is d phi dt, coordinate angular velocity times the Lorentz factor. Now to travel into the future plus b, we need the values of the coordinate angular velocity that are greater than 0, less than this object here. Okay. If d phi dt is 0, then the object is not moving, it's just sitting there, which is not viable. You're not traveling anywhere if that's the case. And b would be 0. Okay, once you start moving though, positive angular coordinates in this range here will take you into the future. Okay, now remember here, this object here, this intercept here is less than this value here. Remember the upper end of the domain, this was less. To travel into the past, that's minus b, which is the clockwise direction on the green curve. If we go in the clockwise direction, which is negative b, the range of the angular coordinate values goes up to and arbitrarily close to the speed of light. When you convert this angular velocity to a linear speed, you'll get the speed of light. And it can go arbitrarily close to it, which is why it's not equal to. Only massless particles could equal that linear speed. And again, less than 0. We can't be 0 because then the observer and their spaceship would not be traveling on our green circuit. The linear speed is given by, just as a reminder, is that radial value times the angular velocity coordinate. All right, now the angular velocity depends upon 3 quantities. So f, here's f again. Okay, our value of f, not just the angular, well, it does, it depends on that, but if I was substituting in here, let's start with f first, then we'll get down to the angular velocity down here. Substitute all that in, we get this quantity here, which is negative, which is why the quadratic graphs are being concave down, because overall in this region, this is negative. This middle term dominates for small values of r0. Middle term here is positive, and this last term here, the intercept, is negative. Okay, so it has roots d phi dt. These are the roots. Okay, substituting that in, you can see that it depends on 3 quantities. We have mass, m. We have a, which is the angular momentum, angular momentum per unit of mass. Okay, and All right, and then one other thing is, okay, now, so using our second example of a 21.2 solar mass black hole, and this time with R0 as 0.15, 15% of the radial value A. But now we're going to vary the dimensionless spin parameter, which is A star. I should have written that there, but I didn't, but it's A subscript star, as you can see here. Now, 21.2 solar mass black hole. I've looked at this for R as 0.1A, but this is now for R as 0.15A, and we get this curve here. Again, most of it's all negative with the one intercept here in that region that's positive. If we go down even smaller, we get A as 0.2 here. You can see the parabola is starting to close up. It's gone from an expanded parabola, which is dilating away from the f-axis and towards the horizontal axis. Now it's dilating here with a smaller value of A towards the vertical axis and away from the horizontal axis. Go again very small, getting closer to 0 here, and the parabola very much closes up. Okay, very much closes up, but still has two intercepts. They all have two intercepts. And also, if you notice, changing the value of A has changed the scale. If you look at the plots here, the scale has been changed. Very large here for a small value of A, for a larger value of A getting close to 1, a smaller range of values for the angular coordinate. Now, don't worry about this one too much. The spin parameter, if we take this to be negative, then we're actually saying this now has turned F into something that's entirely positive. It doesn't even touch the horizontal axis. There's no intercepts at all. It becomes entirely space-like. Not to take that one too seriously at the moment, because in the setup of the Kerr black hole there, the coordinates assume rotation in the positive angular sense. If I were to alter the angular coordinate phi and point it in the opposite direction so that the black hole can rotate in clockwise direction, looked at from above, this would then fix itself up, I believe, and would become negative underneath. And I may pick that up in the next video, but I wouldn't worry about this at the moment. It's not a concern. It shouldn't matter whether the black hole rotates in one direction or another. It really doesn't matter. The same structure should form. Okay, it's just a matter of adapting your coordinate system. The coordinate system here that we talk about is for a black hole that rotates in the counterclockwise direction, looked at from the positive z direction. It's going counterclockwise in the usual positive angular sense. If you say that the angular momentum per unit mass is now negative, then you're saying it's rotating in the opposite direction. So you need to adjust your coordinate system. And once your coordinate system is adjusted, instead of the angular vector in the positive phi direction, if we put the angular vector in the negative phi direction, this curve will then become time-like and should be reflected over the horizontal axis and be pointing down. All right, I'll perhaps pick it up in a future video. All right, now let's look at the fast Kerr space-time where the spin parameter is greater than 1. Okay, this is where the angular momentum per unit mass is greater than 1. So if we take A star as 1.2, surprise, surprise, here our curve remains time-like, except at the intercept and beyond. Choose a larger value, 1.8. Again, the graph is dilating away from the f-axis and towards the horizontal axis, but basically, and the scale has changed, going from 1.2 to 1.8, but it's still, for most of its values of the coordinate angular velocity, it's still a time-like curve. Now, what's interesting about this is that in the fast Kerr case, the horizons, event horizons and so on, that structure does not form because there are no roots. Okay, so remember the event horizons occur when there's two event horizons for the inner and the outer. R minus is the inner, R plus is the outer. That's given by this object here. But if A, which is defined, A squared, which is defined as A star, the dimensional spin parameter times GM on C squared. Okay, if that, I should have a square there. My apologies, everyone. That should be squared there. Whoops, there should be a square there as there is over here. Okay, you can see when you put that in here, okay, this gives complex roots. Okay, there's no real solution. So that as I showed 2 videos ago, I think it was, the second video prior to this one, second last video prior to this one, no roots form, and so no event horizons form, and what you have is a naked singularity. Oops, I feel bad about that. There should be a square there. My apologies. Okay, so here, where this A is greater than 1, you get complex roots, no real roots at all. And so this horizon structure, the event horizons don't form, and what you have is just a naked singularity. Okay, so that's interesting then, as I pointed out last video, because you could put a spaceship around that could time travel around that into the past and not be constrained, because obviously once the spaceship crosses an event horizon, it's never coming back to our universe again. But if you don't have event horizons, okay, your spaceship can go into the ring singularity and perform its time travel and return. All right, now using the same example of a 21.2 solar mass black hole with dimensionless spin parameter A star is that one again, same as before. This is an actual black hole. I forget its identity. I've done it in the Kerr video. If you look at the Kerr metric videos playlist, you'll find it there. I can't remember its name. Now we're going to vary R0. So within that ring, we're going to have circles of different radii. Okay, when we do that, R0 is 5% the value of A. We're going to have this curve here. When we go up to 15%, okay, when we go up to 15%, same thing again, same structure. Okay, all that happens is the curve dilates and is rescaled. You get different scalings, although in this case scaling hasn't been affected. Okay, go R0 is larger again, 0.25 A inside, a quarter of the way of A into the ring singularity. Okay, we get this. But if I now set R to negative values, which means I'm now outside the ring, this curve is entirely space-like. This curve indicates the value of f is entirely positive, and so our tangent vector, our four velocity vector, is space-like, and the integral curves to a space-like, which an object with mass can't travel upon. So outside the ring singularity, there is no possibility of traveling into the future or the past because there are no time-like curves. This quadratic value here being positive for all values of the coordinate angular velocity are showing that there's no possibility of traveling into the past or future because there's no time-like curves to travel on. Okay, now, interesting one, we're going to vary the mass. So we're going to take our 21.2 solar mass black hole, we use R0 as 0.1A and the dimensionless spin parameter again 0.9985. So 100 solar mass black hole is going to, yes, sorry, I'm varying the mass. I shouldn't have referred to the 21.2. Here's a 100 solar mass with R0 as 0.1A and A star as 0.9985. Most of the values, F is negative. So we have time-like curves there, as we expect. 1 million solar mass one, curves value. All that's happened is just been a rescaling of the graph of F. But you see how the coordinate angular velocity values change. Okay, shape stays the same. Go to a 1 billion solar mass one. Again, all that happening is a rescaling of the values on the coordinate angular velocity axis. Okay, and again, most of the values for F are in the negative range, so we have time-like curves everywhere for all sorts of values except for the intercepts and that region above the axis. Now, if we were to take something m is negative value, I'm referring here to the exotic mass with negative value. All right, negative mass. So I'm talking about exotic material here. We still get a whole lot of time-like curves. All it does is reflect the graph about the axis F, and what we get is still a whole number of values here where our curve is time-like. So negative mass or exotic mass still has within it, if such a black hole could exist, if it could form and not pull itself apart because it's negative mass, if that could form, you'd have lots of time-like curves within the ring singularity as well. Anyway, leaving that finished. End.